So hi everybody, and thanks for joining this presentation today. The title is Most of the Time It Works Every Time, the mindset behind using probabilistic data structures. And I'm Wolle. Martin just introduced myself. I'm working at the University of Oldenburg, and you can find the slides on my website, which is wolle.science. Before we start with the topic, a brief introduction of what I'm actually doing. So I have been active in the realm of data management, data science, and data engineering for about, 10 years or so. I started at the University of Hamburg, and I there basically started looking at databases and try to figure out what databases are and how the different systems differ, because there are hundreds or even thousands of different implementations, and it's pretty difficult to understand what the distinction between them is, and this is something that you need to wrap your head around when you're trying to do a PhD there. So I worked on database, so OLTP benchmarking with my colleagues, and then quickly turned to NoSQL systems and learned that they are diverse but also pretty lame, in the sense that basically no system at the time was able to handle real-time data. So then I turned to stream processing and built a system, a so-called real-time database, that basically bridges the gap between NoSQL systems and systems that do stream processing, so that you have something like, let's say, update feeds when you build something like a web application. You need a system that does this out of the box, and I built such a system, and then I basically implemented a prototype that went live at the company backend, which is the startup that I then joined. And there I became head of data engineering and research, and we built products to accelerate the web. Now, my vision was that actually this real-time database thing was going to be like the critical part there to make everything awesome in terms of fast websites. Turned out that was not the case, so I kind of basically didn't really keep working on that system, but rather turned to data analytics, and I have the feeling this is something that you often do. You work on something awesome, and then you end up working with data, trying to basically take log data and tracking data and analyze that. And this is something that I do still today, but 2 years ago, roughly, I said, hey, actually what I like is, for example, giving lectures, giving presentations, and therefore I thought maybe it's a good idea to join the university again, and this is where I'm currently working. So I'm at the University of Oldenburg, and I'm working on different things, again, like analytics stuff, but I'm also building systems for data, like data engineering, data management systems and so on. And I'm also very interested in data quality issues, data synthesis, and hands-free coding. I think 2 years back I had a presentation on this as well. And I'm telling you all this because I have a wide range of things that I've been doing over the last couple of years, and something that I always keep coming back to is basically probabilistic data structures, because when you're building systems and you're using them to power real applications, you often find that you need to be efficient. You have a problem and you don't have to solve it precisely, but you have to solve it well enough. And this is something where probabilistic data structures are often used, but in my computer science studies, I basically didn't hear much about them. And this is why today I think it would be nice to talk about probabilistic data structures. And since I'm a university guy now, I decided to make this presentation not on a system that my team and I built, but rather like a mini lecture today. So today we have kind of 3 things that we want to cover. The first is we'll talk about skip lists, because this is just a very awesome data structure. It's probabilistic, and I think it's a good example to illustrate like the idea behind introducing probabilistic elements to a data structure to get certain properties that you can't get without this random element. And that's why we start with the basic ideas. So we talk about what a skip list is and why you want to have something like a skip list, what the basic idea is. And once we got that down, we will notice that it actually doesn't work in practice. So we have to introduce something like a coin flip, some random thing there to make it actually work reasonably well. And we'll talk about what exactly this random element is, why it's important, and what that means for the efficiency in terms of basically a brief complexity analysis. And then we're done with the skip list part, and we'll have an outlook on other probabilistic data structures just to basically illustrate that there are many more problems that you can solve in probabilistic fashion. I try to do this in a way that you don't really have to have much prior knowledge, but there are certain things that are helpful if you know them already. So for example, if you have an idea of data structures like linked lists and array lists, and if you know that there are something like self-balancing trees and hash maps, this is certainly good to follow the talk. Maybe you also have already worked with algorithms, you have done basic complexity analysis, you know what binary search is, things like that. That's also helpful to understand why and appreciate why skip lists are an awesome thing. And also if you have built applications and you have an idea of why simple things like sorting a list and keeping it sorted can be very difficult, this is also helpful to build up some appreciation and hype for the things that we're covering here. And the learning goal for today would be that everybody here has an idea of what a probabilistic data structure is, and specifically like what a skip list is, what coin flipping is in the context of skip lists, and then also what a Bloom filter is and does, what a count-min sketch is, and what the trade-offs or use cases for these different data structures are. So for the skip list part, you can just imagine a simple application scenario like this. So imagine you have a list of key value pairs, so you see the numbers there. Those are the keys, so primary keys or user IDs or something like that. And then you have values attached to them. So here, these are usernames. And the skip list is basically a list that is sorted. So you have the key value pairs sorted by the keys, so by the numbers there. And you want to keep them sorted throughout the lifetime of that list. And for example, I think the Redis sorted set implementation uses skip lists, but you have also could also think about something like a Discord server that wants to keep the users somewhere in memory or something like that. And maybe as an important note, for the examples, we're not visualizing the values, we only visualize the keys because the slides get bloated otherwise, but you can always think of the numbers that you see there as a key value pair where you see the key but not the value. Yeah, as I say, the challenge that skip lists try to solve here is maintaining order. So you have a list and you want to keep that sorted, and now you may ask yourself, okay, but why shouldn't I use a standard list? Like for example, a sorted list, or maybe also a sorted linked list or a sorted array list. And there are good reasons against those standard implementations. Let's start with a linked list here. If you want to search something in your linked list, that means you have to basically iterate the entire list. You have to traverse every item there because you don't have direct access to the individual cells. So the search time complexity is linear, or in O of n, which means if you have a list twice as long, your search is typically twice as long as well. However, once you have the position where you want to do an update, doing the update is very fast because you can just bend pointers and insert a new element anywhere. So we have basically constant time updates after you have done the search to find the position where you want to do the update. With sorted array lists, it's basically the other way around because the search is pretty efficient. We have direct access to the individual cells here, so we have logarithmic time complexity. Imagine we want to find, let's say, the key value pair with the key 6. We could just start in the middle, and then we see, okay, the middle, then we just hit 17. But now we already know, since this thing is sorted, we don't have to look at the right half. So we just check the left half, and then again check the middle. Okay, it's a miss again, but we know since this is 9, again, we're only interested in the left rest, basically, of what we haven't looked at so far, and then we hit the 6 in the next try. So this, having a list twice as big would not double your search time. However, updating things is the super lame, because to insert something in the middle, you have to move all the values or the key value pairs following the position where you want to do an insert to the right. So this is basically linear in complexity, and this makes both list implementations bad for maintaining order if you want to find things quickly. Because we have fast updates in the linked list case, and binary search in the sorted array list case, but we can't have both. And the question is, can't we have a list that gives us both? And the obvious answer is yes, we can, because otherwise I wouldn't be building up the hype for skip lists so much. And the idea of a skip list is basically to have a linked list that gives you binary search capability. So what you see at the bottom there is the basic skip list starter, let's say it like that. So we take a normal linked list, where we just should traverse the entire list to find something, but now we introduce shortcuts. So the ability to skip items, hence the name, skip list, because we can skip portions of the list. And we do this by adding additional layers to this list. And the bottom normal linked list thing there, that's called the normal lane. And then we add express lanes on top. So the first level there, this is the nodes here just grew. And now you see that we have multiple pointers for some nodes here. The first express lane, so level 2 basically adds pointers so that we skip every second node on the lane below. And then we add another express lane that again skips every second node on the lane below. And we do that until we end up with a single node lane. So now we basically have additional lanes on top of the normal linked list, and every additional lane has half the nodes that the lane before had. And this is cool, because if we want to find something in this list, we start on the topmost express lane. In this example here, we're looking for the 19, and then we basically enter the list on the far left in the top express lane, and we keep advancing until the next step would overshoot. And in this case, the first step would already overshoot because the first node on the express lane at the top is 21. And that means we go down one step and then say, okay, the next node would be 9, so this thing here. And then we would check the next node and see, okay, we can't progress on this lane because now going to 21 again would overshoot, so we step one down and then go to 17. And again, next node would be 21, so that would be overshooting again, so we go down one node, one lane again. And we do this until we reach the node that we're looking for, or until we reach the normal lane and overshoot, because then we know the key that we're looking for isn't in the list. And if you think about this, it means for every search, for every search, there are log n levels, because we cut the number of nodes in half on every additional express lane. And every search will visit 2 nodes at most per lane. This means that the overall complexity is logarithmic because we don't visit more than 2 log n nodes per search. So what that gives us is basically a linked list where we have logarithmic search complexity. But the cool thing is we also have linear space complexity because the overall number of pointers in our list is no more than 2n, so twice the number of key value pairs in that list. And just to explain how that is, think about like counting all the nodes, all the connections in your list. You basically have all the nodes on the normal linked list, so on the normal lane, and then you have half of all nodes on level 2 and half of that on level 3 and so on and so forth. So if you sum up all the nodes on all the different lanes there, you get something like this here, and if you're a mathy girl or guy, you will notice that this is a geometric series, and you can simplify this to 2n. So that just means we have a binary search capable linked list, so we have the best of both worlds. Awesome. But so far, we only talked about the list that we have and we want to do search. The thing is, we also want to update the list. So the question is, can we do that efficiently? And for some updates, this is possible. So for example, if you just want to update the value, change the username, this is easy because you do the search and then you have found the right key value pair by ID and you change the value, done, You can also insert things, and sometimes that's efficient. So for example, imagine you want to insert something like 27. You can just put that thing at the back of the list. Easy, very simple update. But sometimes updates are also very lame and very inefficient. For example, inserting 20 here would be extremely expensive because it needs to be here directly following the 19. And that means, because we have this requirement of skipping every second node on every level, that now we need a node like the 21 node, but it should be the 20. And then the 21 node should actually be like the current 25 node here. You see the problem is if we want to insert the 20 now, we basically have to wire up everything from scratch. Like we really have to touch a lot of stuff here, and this is not good. So that's the problem. Having this perfect skipless structure is good, but it's very rigid in the sense that you can't update it efficiently. So, this is where the probabilistic part comes in, because the idea is good, but doing this precisely is just not practical. And the solution is that the current requirement of having exactly half of all nodes being promoted, if you will, from one lane to the next, from the normal lane to the first express lane, and from the first express lane to the second express lane, and so on, we would just relax that and say, okay, we don't do it exactly, we don't cut it in half exactly, we do it on average. So if we do it on average, we would expect that everything remains the same. On average, search path should still basically be the same as for the perfect skip list, but not every time. It could also be that we have a skip list that is very slow. Shouldn't happen, but maybe. And the way that we now decide how many pointers we add to any node, here the one with just one connection is level 1 node, and promoting it, when I say that, what I mean is that we add the node to another lane. So we have nodes on the normal lane, or we promote them to lane 2, then we also have like 2 pointers here. And the decision whether we do this or whether we don't do this doesn't depend on the structure that we want, but just on a random thing, and this is a coin flip. So we basically, when inserting a node, we just have some promotion probability and basically flip a coin to decide on how many lanes this node should be visible. And in the following examples, what we have here is basically the coin flip. Heads means we promote the node, and tails means we stop and don't promote it further. So let's talk about how the updates that were inefficient in the examples that we just had are now more efficient with the probabilistic case. So if we want to delete a node, so for example, 17, what we do here is we perform the search just like we did before, and then find the node on the normal lane. So we do the search, and we go all the way down to the normal lane so that we have basically done the search all to the bottom. And the important part here is that on our way down through all the express lanes to the normal lane, we remember all the predecessors of the node that we are trying to find here. So imagine we delete the 17. What we do here is we start at the express lane here, then say, okay, first node is the 6, and then there is no further, no successor node. So the 6 is basically the first node that we remember. This is the vector here. And then we go to the next level, and since we are looking for the 17, and the next node here is the 25, we also know that the predecessor of the 17 would also be the 6. This is why we have the 6 here as well. And then we do this all the way down until we have this vector that tells us what the predecessor is on every level. And here is a node. This may be important. On this level here, once we reach 9 here, we could also reach the 17 on the express lane there. But it's important that we have the predecessor on every level. So in the delete case here, we go down to the normal lane as well, because we need to know that the 12 here would be the node directly before the 17. So, and this is important because if we now remove the 17, there's something missing here, which means, the connection between the nodes that are basically connected by the deleted node, they need to be updated. So we basically now use the vector here that remembers all the predecessor nodes to wire up the nodes that were basically surrounding the thing that we just deleted. Okay, now we have deleted an item, and that was pretty fast, and it's fast because we simply don't care that the skip list structure isn't perfect anymore. But if you think about a list with 100K items, it doesn't really matter in the grand scheme of things. This is like the main aspect of this thing. And now if you want to insert something, for example, if we want to reinsert the 17, we do something similar. So we again search the position where the 17 would be, all to the bottom, like we did right now. We also remember the predecessor nodes, like we did right now. And now we insert the node, and we need to decide on what levels we insert the node. So is it just on the normal lane? Is it also on the express lanes? And so on. So we flip a coin. And every node is on the first lane, like on the normal lane. So we know it's at least in level 1 node. Then we flip the coin. Let's say we get heads. So we also add it to the second level. We get heads another time, so it's level 3 node. And then maybe we don't get heads anymore, but tails. So we know, OK, it's a level 3 node. And then we would just put it in here. And since we have this vector that remembers all the predecessor nodes of the position where we want to insert, we can now do all the wiring and just connect all the nodes to the one that we just inserted. And you see here that the green and yellow arrows are basically the stuff that we need to update. But it's basically still a constant time operation because we have at most in this example here 4 levels that we have to touch and just 1 node that we insert. Yeah, so this is all in all a good thing because we have a list that on average should be good enough, because it has these properties that we talked about of logarithmic search complexity and linear space complexity on average. But we still could tune this thing by changing the promotion probability. I just talked about flipping a coin because I assumed a 50-50 chance, but we can also say we take a higher or a lower promotion probability. And just for illustration purposes, we have a table here that shows you different promotion probabilities. Here you see 50%, so this is the coin flip, and here you have basically decreasing promotion probabilities. And what you see is that the time complexity, here the 50-50% case basically is the baseline, so this is 1, and you see that here is relative to the baseline. You have different time complexity values, and on the right you have the space complexity in terms of pointers per node. What you see is if you decrease the promotion probability, so the likelihood of a node getting promoted to the next express lane, it increases the time complexity. Basically, just ignore the Euler number case here because it's such a special number. But if you, intuitively speaking, if you say, hey, we have 50-50 chance of a node adding the next express lane, you just have like a denser tree structure in your skip list. And if you have a very low probability, let's say here 1 by 16, you see that it's twice the time complexity because you would just expect the search paths to be longer, because you have fewer nodes in the express lanes, so you have to iterate through the individual lanes just longer. And at the other side here, you see if you reduce the promotion probability, what you also get is fewer pointers. And that means you have just a more compact data structure because you don't have as much information, so fewer pointers that you need to store. And this is basically the trade-off in this data structure here, better storage efficiency with decreasing p-values and increasing or slower search time at the same time. And we talked about this on average thing quite a lot. I always say, it's logarithmic time complexity with high probability or on average. And the question is, what's that probability? Because, of course, you could just have, even if you have like a coin flip, you could basically have every node on every level. And then you just have a linked list with additional pointers, and it's just super slow and super inefficient storage-wise. So it's interesting to know how likely it is that you actually get degraded search performance. Because with some probability, search might be slow, and with some probability, you can get this worst-case scenario. And from the original skip list paper, there's like this nice illustration. And what you see there is in the different line, let's say, colors and thicknesses and gradients and so on, you have different list configurations. And the interesting part here is the y-axis, because this is the ratio of actual to expected search cost. So on the left, the 1 means this is the likelihood of you getting a search that is exactly average search performance. So like the search path is of average length. This 2 here means search path is double the expected length. And the 3 here means search path is 3 times the expected length. And on the y-axis here, you see probabilities. And what you see here, just for reference, is likelihoods that correspond to things like, you go to a random green field and then pick a clover, and you get 4 leaves on first try. Or you buy a lottery ticket and win the lottery. And here at the bottom, so way more improbable, is that you have a search path that is 3 times longer than the expected search path for a skip list with 4,000 items. This means you can still have a search path that is 3 times as long, but if you look at the numbers here, what you see is the likelihood of this happening decreases dramatically with, for example, list size. If you have a list with 4,000 items, having 3 times the search path isn't that bad because it's just 4,000 items. If you have a list with, let's say, 4 million items, then the likelihood of actually getting a search path that is 3 times as long is just abysmally small. So the bottom line basically is, if you have a skip list and you have a very small one, then you don't care that much about whether or not you're hitting average performance, because even deteriorating performance isn't bad. And if you have a very large list, then the likelihood is so small that as soon as you start worrying about skip list luck deterioration, you should also be worrying about flipping bits, basically. Yeah. Hello? Yeah. But chances are you already visited, for example, a database lecture in your life. And you may have noticed that everybody's talking about trees and nobody's talking about skip lists. And trees also have linear space complexity and logarithmic time complexity. And they also provide basically worst-case bounds. So you might be asking, why, oh why, should I be using skip lists? And this is a good question, and hence the original paper answers this question. And the author says, from a theoretical point of view, there is no need for skip lists, which is already good if this is your own thing, Because balanced trees can do everything that can be done with skip lists, and they have good worst-case time bounds, unlike skip lists. So this is not very encouraging, but I think it's still reasonable to talk about skip lists and use them, because compared to tree implementations, they are very easy to build. They have simple operations. You don't have to do rebalancing, because if you talked about, or if you had a lecture on tree indices, then you may have noticed that they are wildly complex, and this rebalancing operation all the time is just mind-blowing. So if you can't use a library, then building yourself is way better with the skip list. And also, they are very robust, because with trees, you can have sequences of records that you insert into your tree, and just this sequence breaks the tree in the way that you always have to rebalance. You don't have this with skip lists, because skip lists are, the probabilistic element there is independent of the insertion order. On the other hand, the benefits of trees is that they are very predictable, because they have strict worst-case bounds. So you have guarantees that performance cannot deteriorate beyond a certain threshold. And also, they are just more efficient, because with the skip list, you basically have binary search, but with trees, you have a way higher branching factors, so in practice, they are just the better implementations. But for teaching purposes, and also if you implement this yourself, skip lists are still awesome. And if this were a real lecture, then we would be talking about more things, for example, about advanced skip list variations. We would be talking about optimizations and go into more detail on this complexity analysis thing. And perhaps we would also do something like, hey, please implement your own implementation. And then we do like a performance shootout or something. And we would also be talking about other probabilistic data structures. And actually, this is the part that I would like to close with this mini lecture today, because I think now that we have seen like a thorough example of a probabilistic data structure, seeing two other examples might be nice just for you to appreciate that there are other problems that you can tackle with such a probabilistic approach as well. So let's change the challenge slightly. Until now we talked about something like a user list, and we want to keep it sorted. Now let's talk about a user list, and we want to check whether a user is, for example, logged into a server. So imagine you have like a huge Discord server, and you want to know whether somebody is currently there. What you would actually do is you check the database, and like for example, let's say it's a registration problem. You want to register, and you need to check whether the name is still free. Maybe that's a better example. What you could do now is you ask the database every time, or you build a data structure, this Bloom filter thing here, that basically encapsulates the information of every username in the database. And the example here is you have a simple hash function that's just taking the first letter of every name, and you have 1 bit for every letter in the alphabet. So what you have here is basically a Bloom filter that indicates whether or not there is somebody with a username with that starting letter. Obviously, it's a simple example, but in practice, you could take just a more complex hashing function, and you're good as well. And if you want to check whether your username is still free, you could just ask the Bloom filter first, and only if you're not sure, you could then ask the database. So, when there's a new user, the server computes the hash for this user, or hashes, if you have multiple hash functions there, and then you check the Bloom filter, and if the Bloom filter says, yeah, there's somebody with that starting letter, you have basically a hash match, then you need to ask the database. But if the Bloom filter says, no, there's nobody with this hash signature, then you know that the username must be free, because otherwise your Bloom filter would tell you. So you basically verify the uniqueness only for positive lookup results in your Bloom filter. So if you, for example, want to check, okay, I'm Zach, I want to register, is Zach still free? You just check whether there is somebody with starting letter Z, and if this is not the case, then you don't have to check the database. So this is basically a good thing. And if you, so you basically bypass the database operation here. And if you want to register as Woo, then you would look into the Bloom filter and say, hey, I don't know, there's somebody with W already, so I need to check the database. And then you do that, and then the database can give you the definitive result. But this avoidance of database lookups for obvious cases is super valuable, especially in cases where database lookups are expensive, which might be because you have very many lookups, but it might also be because your database is just remote. For example, in the US, and you're working in Frankfurt. The trade-off here, obviously, is that you have memory efficiency on the one side. So, for example, you have a Bloom filter with just a single hash function, which is super small, but you would, in this example here, get to the point quickly where you have just ones everywhere, and then you just always look in the database because your Bloom filter doesn't really help anymore. So this would be lame, but it also just increases the false positive rate. So if you get a negative, so if you do a Bloom filter lookup and you see that there's nobody there with this signature, then you are safe to use that information. And the tuning, so basically increasing or removing, like lowering the false positive rate at the cost of memory efficiency, can be done by increasing the number of bits. So in this example, having more columns than just the letters in the alphabet, or increasing the number of hash functions. And again, hash collisions just reduce the accuracy in the sense that you get false positives, but negatives are always correct, so you can work with that. And this is a good thing because I mentioned this, I worked at the company backend, and then we accelerated the web with caching algorithms, and the basic premise of the core technology is basically that you can use the browser cache, so it's an invalidation-based cache, and you never know whether the stuff is actually still fresh or stale, because the backend monitors updated resources and tells the client what is still safe to use via a Bloom filter. So, for example, you would load a website and take the HTML, and then you could reload the HTML, or you could take the HTML from the cache, but there's a Bloom filter that tells you whether the HTML is still up to date or not. This is like the basic idea. We have papers and talks on this, but this is something where I actually used the Bloom filter in practice, and came to love it quite a bit. Another probabilistic data structure, and this is like the wrap-up data structure here, is the count min sketch. And the challenge here isn't checking membership, but rather checking item frequency. So imagine you have a server and you want to know how many messages were sent by every individual user. The basic problem would be that you just have to have one counter per user, but if you have very many users, that's a lot of counters. And the idea here is instead of storing one counter per user, you would store basically one counter per hash. And then you just have to have like you have to have an array of counters. In this example here, again, the columns are the letters of the alphabet, and now we have two hash functions. To illustrate it better, the first hash function takes the starting letter, and the second hash function takes the last letter of a name. And if we want to basically check the counter for a user, we always hash the user by all the hash functions and thereby identify counter positions. And we either take the counters that we find or we take them and we increment them depending on whether we query or whether we insert. So for example, if we want to know, if we want to register a new message by Fabi, we would hash Fabi, because that's the user. So we take the counter in these two positions there, and then we just increment them. And since we know that every time that Fabi sent a message, we increment the right counters, we could also do it reversely, and then know that the counter value that is there is basically like an upper bound of the messages that Fabi sent. Because we know we never registered too few messages, but we could have increased the counters because there's a hash collision. Because here, for example, if we want to query volley, we would do it the other way around, and then just check the counters for volley, and then take the values that we have there, and we take the smallest value, and then this is like an approximation of the actual count that we have. So the cool thing here is basically, again, we have a compressed representation, which is like fixed size because we can define the number of counters that we want to have. And depending on how many actual users there are, we may be overcounting, but we know that the space requirement for us to do this is actually fixed and nothing will blow because we have so many users. And we can increase the precision, so reduce the overcounting error by increasing the number of counters or adding additional hash functions. And the cool thing here is that every count that we get from this is an upper bound, so we know that the actual number might be off, but it's never smaller. And that's basically the talk. So in the first part, we talked about how awesome skip lists are, and I hope you agree that they are pretty awesome. They are simple and straightforward to implement, and you could rather easily extend and modify them, for example, because you change the p-value or whatever. They are efficient, they are logarithmic in time complexity with high probability. What that means is also something that we talked about, and they are very robust in the sense that you don't get bad input sequences as you may get them for trees. And there are other probabilistic data structures that are useful in a variety of applications. For example, as we talked about ordering things with skip lists, or you can do efficient membership tests. With Bloom filters, you can estimate upper bounds for item frequencies, or the example with the messages per user, with account min sketch. And there are many more, which we didn't talk about. I think one of the more notable ones would be the hyperlog for counting unique visitors, for example. I didn't include this because the slide was getting wild, and we only have so much time, but maybe next time. Yeah, and that's my presentation. Thanks for your attention, and I would be ready for questions now.
That was really cool. I also love that everyone is still there, because I would have thought that it's so much that half of the people leave. I also loved how you said "obviously" at 2 times, and I was like, no. No, not obviously. But that's the cool part about the code talks, is like I meet so many people that are so much smarter than me. But yeah, I have a few questions. Does anyone have a question other than me?
Yeah, I would have a question. Did anybody ever use probabilistic data structures here?
I know I didn't.
Like, was that a hand back there?
No.
Okay, I see one hand. Wow.
I remember that there's like, I think everyone most likely knows like this interview questions that Google supposedly does when they are like hiring you, and then there's like, so how do you do this data structure? And I feel like now I'm prepared. Like from my perspective, honestly, I think the main question is, yeah, if you are creating your own. Oh, by the way, I have to connect you with a friend. You have to tell me that because he also keeps on telling me about like data structures a lot. Anyway, so mainly the main thing is like, as a developer that's more in front end, more doing like normal back end work. Obviously, it's good to understand how, for example, data structures under the hood are working.
Obviously.
And I think it's a good brain training. But like, for me, like as a normal engineer, like where's the main use case for that? For like these data structures outside of database? I
think you don't have to understand how they work. You have to understand what they bring you. For example, you have this Bloom filter thing, and it's like a set. You use it like a set. You insert stuff, and now you can check whether it's in there. And you just have to know if it says, yes, it's in there, maybe false. If it says, no, it's not in there, definitely true. So for example, assume you build a cache. You have a website, for example, and you have some Bloom filter that tells you all the resources that have been updated by your deployment, for example.
Yeah.
And then you reload the page, but you also have this Bloom filter that tells you like everything that has been updated is in there. If you check like an image and you check whether it's in the Bloom filter and it's not there, then you definitely don't have to update it. So this is something you don't have to build it. You just have to know if this is false, then I don't load. And I think this is super helpful. And like in the backend case, for example, the Bloom filter is like few kilobytes, so it's very, very small. And if you don't update 100K resources, but only 10 per deployment, then this is a super valuable thing because you deploy without really killing page load time. For example, cache busting everything, and then you have to reload, and after deployment, this is rather lame. You can circumvent this by something like a Bloom filter.
That's how I handle cache problems, honestly. But I can understand. Okay, so I think no other questions so far, but also we are a bit pretty close to the time limit.
Yeah, wait, is that a question there?
That's a question? Ah, sorry, I didn't see 4. I'm sorry.
Just coming up. Thanks, Wolf, for the presentation. It was pretty great. One question I have is, since we were talking about key value pairs, if you were searching for the value in your skip list, since we only went through the keys, and sure, you can always check if it's smaller or bigger. If I were to search actually for just the value, how would that work?
Well, I would say if you just search for the value, you need to traverse the entire list because the value is basically random in this here. What you would do there is if the value is actually the important thing, then that should be the key.
Fair enough. Okay.
Yeah. Thanks for the question.
Okay, any other questions? If you like this level of complexity of talk, there is a hackathon on quantum computing tomorrow. No, I made sure that they keep it easy, actually. Like, there was a lot of back and forth. But thank you so much, Wolle. That was so cool. Yeah, thank you.
Thanks.
And
as well.
let's
Bye.
give him a hand.